Okay, I'm going to start. And I read 16. I guess people will come later. Okay, can you hear me clear?
Yes.
Very good. So the last subject we were talking about, it was the public key cryptography, and in particular, it was the beginning of the digital signature. The digital signature, it is a very articulated topic because there are a lot of aspects that should be considered. Most of them have been already described. I talked to you about digital certificates. If you remember, the current standard is named the X509 version 3. And a certificate is a document stating a lot of information, but the most important is the public key and name. This is a correspondence between a public key and a name. And by means of this digital certificate, you can get this correspondence. About this, I told you that there is the certificate is a digital document containing several fields. And this digital document here is showing the digital signature of the certification authority. So it is signed. This means that we can trust this document because the signature of the certification authority can be verified. I will tell you more about this, but it is important you start entering this type of details. And I want to also tell exactly again what the digital signature, the original digital signature is. And today there are several other approaches, but I think that the RSA approach, that is the historical one, is the easiest to be understood, and it is easy to understand all technical details, because we discussed already some facts. I want to remind. There are P and Q, prime numbers. Random. And we call big N the product, P times Q. And we also told that the problem of given n, find p and q is hard. Factorization of n is hard. Keep in mind that n is a number containing thousands of digits. So maybe you can say that it is somewhat easy to factorize a small number, but when the number is having thousands of digits, the problem becomes hard. In particular, the attacker is knowing n, big N, but doesn't know P and Q. Instead, the designer, the owner of the private key and the public key, is knowing both N and P and Q, of course. And we call it also another quantity that is called the phi o n. And this is p minus 1 times q minus 1. And this is called the tangent function. In many cases, since n is fixed in some way, people just write phi in this way. Okay? Now, for constructing the keys according to the RSA algorithm, we choose a number E that is between 1 and phi of n randomly. But the condition that is wanted is that the greatest common divisor between E and phi is equal to 1. Mathematicians say that they are coprime. And now there is the problem of finding a number D such that D times E is equal to mod. Oh, I forgot the mod. Mod phi is equal to E times D mod phi, and this is equal to 1 mod phi. And we used to say that D is equal to E to the power of minus 1. Is the multiplicative inverse of E. Of course, it is also true that D to the power of minus 1 is equal to E. The meaning of this is that whatever we consider D or E, one is the multiplicative inverse of the other. So their product is always giving 1 as a result, 1 mod phi. Okay? This is very important. Keep in mind that phi is the product of these two numbers. It is slightly less than n. And this is the definition. And typically, we say that the pair E N is public. This is the public key. And the pair DN is the private key. You know that the private key is kept very private and should be not compromised, should be not seen by everybody. It is really private. It is only the value of D that is important, because you see that the pair En is public, so the number N is public. And the definition of the encryption operation is that we want to encrypt a number. This number is a number we want to call M, that is not greater than N, is less than N. And this is obtained by the encryption. It is obtained by computing M to the power of E mod N. And the decryption, and this is giving what a result, we call it C. And the decryption is obtained by computing C to the power of D mod N. And this is giving back M. So you understand that M should be a number less than N, because any mod of N is less than N. The mathematical explanation of this property is not really interesting to discuss, because it is a little bit involved with some discrete mathematics. So to explain every detail is going beyond our purposes, but this is important. So this means that we can distribute the public key and this other key is to be kept totally secret. Okay, we already discussed the meaning of encrypting by using the public key and encrypting by using the private key. In this example, we are encrypting by using the public key. This is public, so we can decrypt by using the private key. But we can do also the opposite. We can encrypt by using the private key, still mod N. We can decrypt by using the public key, C to the E mod N. We also discussed that we can obtain two different properties. One is providing confidentiality. If we encrypt by using public key, we get the confidentiality, because only the owner of the corresponding private key can decrypt and cannot give this key to any other person, because in this case the key would be compromised. And vice versa, if we encrypt with the private key, we can do that because we are using our private key, everybody can decrypt because can use the public key, but so we don't have any confidentiality, but everybody will understand that it was me doing the encryption. And this is the basic mechanism of RSA. Is it clear? Are you with me? Yes. Any question? Seems no. Okay, there are two important points to discuss now. Forgery and key revocation. So let's discuss first forgery. The idea is that we can, when Alice is sending a document to Bob, imagine for now, just for now, that Alice is sending a number to Bob. And Bob can check the number. I mean, if Alice is sending a pair that is number M and the signature S, where the signature is the result of this encryption, this is S. Okay. So Alice is sending to Bob this pair. And Bob can do the verification. How is this verification? First, Bob is decrypting S. So Bob is computing S to the E mod N. Can Bob do that? Of course, Bob can, because it is necessary to know the pair EN, but Bob is knowing the public key. So it is no problem in computing this decryption. And then for now, let's imagine, let me open a parenthesis. Let me write another color. I want to show you the result of a wrong definition. Wrong definition. Def. The digital signature of M is given by M to the D mod N. Assume that this is the definition. I told you that this is wrong because incomplete. But let's assume that we give just this definition because we think that if we are encrypting by using the private key, we are just proving our identity. So we don't see any reason for not adopting this definition. This is seeming very natural. But there are several problems in this definition. And the first problem is performance. Because big M implies a long time. Because that mathematical operation, that is the exponentiation, is a very tough operation. It is requiring a lot of time, and the longer is the document we are signing, the longer will be the operation. So this means also that it is not sustainable, and this is there is also a lot of energy consumption, and this is leading to battery draining in many devices. So there is a practical problem, but there is a more serious problem, because it is possible to do a forgery. What is a forgery? A forgery is an operation that now I will show you by using this wrong definition of digital signature, okay? This is the wrong definition of digital signature. So let me go back. I was talking about the check of Bob. Better, I want to call it a verification. So Bob is doing the verification. So Bob is decrypting this digital signature, and the result of this digital signature, it should be M, right? Because we got M by the other operation, M to the D mod N. So this is the inverse operation, right? And this is meaning that we should have a non-repudiation. Is this clear? If you have questions, make questions, because this is very important. You want to think about that? Let me write also that S is equal to M to the E mod N. This is the pair Alice is sending. So Bob can do this opposite operation, inverting the signature, so that Bob can decrypt the ciphertext in this way, S to the E. Sorry, I used the wrong symbol. It is not E, but D, because this is the private key. So Alice used the private key. And Bob can verify by decrypting the message, so that he get back a message M. Let me call it M prime. That is the result of this operation. Now the question is M equal to M prime? Yes, no. Accept, reject. Okay, so this is the verification. It is a verification algorithm used by Bob. So Bob is not really a user that is thinking, analyzing. It is not a mathematician. It's just a user, and Bob doesn't even know how the verification algorithm works. But we have the fact that the verification algorithm is saying, okay, accept. And so that Bob will accept the signature. If accepting the signature will have a legal value and it is accepted for any legal reason. If the verification is providing a negative answer, just Bob is not accepting the signature. So the document will have the value of an unsigned document. Okay? If the verification fails, the value of the document M is just the value of an unsigned document. And this is the meaning. Okay?
Yes.
Now we can define more precisely what a forgery is. Forgery is the ability of attacker to produce a pair A-B that will pass the verification. Meaning pass means that the verification is answering yes. Okay? Now let's see why the definition we gave is wrong. Because it is possible to do an attack. Let the attacker generate a random file. That is B. Now the attacker, of course, the attacker can do that. It is easy to generate a random file. Now the attacker can compute the decryption of file B by using the public key of Alice. And this is A. So the attacker will send this pair now, A, B. So that when Bob is doing the verification, Bob will decrypt B by using the public key of, you understand that encrypt and decrypt here, it is the same because it is the same operation. It is an exponentiation, just it is different what exponent you are using. But basically it's the same operation. So I will use encrypt, decrypt with the same meaning. So Bob can check that by decrypting B by using the public key of Alice is providing the value A just because this is true by construction. So the verification work. You can have an objection by saying, okay, the attacker can compute in this way A, but perhaps A is meaning nothing because it was just computed by an algorithm. It is not really meaning anything. This is why we call this forgery, we call this forgery existential forgery. Existential forgery. And we say that it is when it exists a pair AB produced by attacker that passes verification. Okay, this is the existential forgery. So the attacker is able to construct A. What does it mean, A? Maybe nothing. But it is able to pass the verification step. And this is the important part, because if this is allowing to pass the verification step, Bob will accept. And then Bob maybe will be asking, what is the meaning of this message? I don't understand, but the verification was good. So it is important that the attacker is not able to do an existential forgery. Technically speaking, there are more powerful types of forgery. A more powerful, let me call for shortness, existential forgery, EF, existential forgery. There is another type of forgery, selective forgery. It means it's very similar to existential selective forgery. Very similar, but attacker can construct a few pairs, A prime, B prime, or A double prime, B double prime, or triple prime, or B triple prime. How many? Not many, just 4, 5, 6, just a small number. And any of them, each of them, passes the verification. You understand that existential forgery is less powerful of selective forgery. So it means that if you are able to do a selective forgery, you are also able to do an existential forgery, but not vice versa. If you are able to do an existential forgery, it is not necessary that you can do also a selective forgery. Maybe the pair you have found to pass the verification is a unique pair. The most powerful type of forgery is the universal forgery. And we define it in this way, the most general way. For each A, the attacker is able construct the pair A, B, passing the verification. Of course, this is the most powerful because whatever you choose A, you can construct the correct signature and then you can pass the verification. This is the universal forgery. This is why universal forgery. This is why we write that existential forgery is less powerful of selective forgery. It is less powerful of universal forgery. Okay? By using the basic of mathematical, I don't know if you know the logic, but if you want to write in an equivalent way this property, you can write it by saying if you are not able to do a universal forgery, and we write it this way, not universal forgery, then you are not able to do a selective forgery. Then you are not able to do an existential. Sorry, I wrote in the wrong way. Let me rewrite. I use this principle of logic. P implies Q. We can read this also like implies. And this is equivalent to say that not Q is implying not P. These are equivalent. So if we use this equivalence, we can write that not existential forgery. Sorry, the direction of the arrows is wrong. Universal forgery implies a selective forgery that implies existential forgery. So if we use this equivalence, we can write that not being able existential forgery implies that we are not able to do selective forgery. That is also implying that we are not able to do universal forgery. Where I wanted to arrive? I wanted to arrive that we are happy if we can prevent the existential forgery, because if we are able to prevent the existential forgery, we are able to prevent also more powerful types of forgery. This is a very important question. And we obtain this by changing the definition of digital signature. So we can now the definition of digital signature. Correct. So assume that we want to sign Alice wants to sign M. The first thing is that Alice uses a cryptographical hashing function that is been selected. It is known. It is public, so everybody knows what is this hashing function, and computes h of m. This is equal to small m, where h is cryptographic hashing function. Do you remember the properties of cryptographic hashing functions? The most important, the unique two properties is they are one, not invertible. Means that it is not easy, it is very hard to invert the function. Given small m, it is hard to find big M. Second, resistant to collisions. Okay, this is meaning cryptographic. So, 3. Signature is small m to the d mod n. So you will see that the only difference with the old case is that we are not using as a base of the power big M, but we use the hashing value to be raised to the power of d. This is providing a lot of beautiful properties. First property is that the hashing value is a small value. Whatever is the size of the original number m, small m is a smaller value that is having a fixed size, and this size is very small. This is meaning also that when we are computing the exponentiation, we are not facing a very hard problem, because we are computing the exponentiation of something that is a smaller value and not a big value. So it is less passes. And this is a very important property. Also, if we try again the attack of finding the existential forgery, we must solve a problem that we are able to generate a random signature. We can invert the signature and find the digest that is the result of the hashing function. But now we are faced with the problem of to compute the inverse of the hashing function. But since the hashing function is cryptographical, we cannot invert it. So the adversary is not able to complete the attack for finding the existential forgery. So it is now hard to do the existential forgery. That is what we want, because if it is hard to do the existential forgery, it is hard to do the selective and the universal forgery. And also we are better performances. Okay? So this is the definition. This is the signature, capital S. And then send pair M, sorry, no, exact, send the pair M S. Now we should understand how the real verification works now. First, Bob is computing the signature S to the power of E mod N. And this is providing small m, that is the digest of the message. Then Bob can take the original message M that is has been received and can compute the hashing. Let me call the first M small m M prime. And now Bob should check whether M is equal to M prime. Yes, no. Accept, reject. Okay, this is the verification. So we can move this definition to the general case, meaning that in the general case, also if we are not using the RSA algorithm, but we maybe can choose to use some other algorithm for doing the digital signature. At Alice's side, send M. How to send M with the signature? Compute small m equal to h of m. Encrypt digest. Computing the encryption by using the private key of Alice of digest. This is, by definition, this is the digital signature. So, for sending M, send pair MS. Okay? So it should be clear that when we are considering this setting, whatever setting implying a digital signature, we are sending the original message as plain text. And the signature as a separate file that it can be verifiable by Bob, because Bob will do the following verification. Bob verification. Step 1, Bob receives M prime S prime, a pair. Bob computes h of m prime. This is m small m prime. 3. Bob decrypts S prime by computing decryption by using the public key of Alice of S prime. And this is M double prime. 4. Is M prime equal to M double prime? Yes, no. In case of yes, accept. In case of no, reject. Is it clear? I want you understanding that the digital signature is composed by digital data. I described you the digital signature as a file, okay? So when you are printing a document, you cannot print the digital signature, meaning that if you print the document, you are not considering the digital signature that is lost in that moment. It is lost. It is not on the print. The digital signature is only a file that you should save with the document, and it is important you are saving both the document and the digital signature. And the signature is a file, not printable. It is true that there are projects where they found a way to print the digital signature by using a QR code or other type of visual code, but it is not important for us. Now it is important that we understand the meaning of the digital signature. It is a file, okay? It is very important. When you print the file, you are losing the digital signature, because the digital signature is not normally printable, because it is a sequence of 0, 1, and you cannot give any meaning to this sequence. Okay? Any question? Another point. We have assumed that we want to sign a number. Less than n. But what if m is a text? So if we consider m as a text, of course the text is a sequence of bits. We can consider this sequence of bits as the representation. Consider the sequence as the representation the binary representation of a number. So you should understand that there is no difference between a text and a number. Whatever text can be considered as a number. Just the problem is that if the text is too long, the number will be too big, and maybe it is larger than n. In this case, we should separate the text into smaller text, and we should use modes of operation. But this is not happening when we are doing the digital signature, because we are encrypting a digest that is the result of a hash, and the result of a hash is always small, so that we are sure that the number will not be too big. Okay, so we will not need any mode of operation while doing the digital signature. And this is important. Okay? Any question? Do you want to think about that, or is it clear? This is the verification, and this is the signature.
It is clear, thank you.
Now, I want to tell you that in all the world, mostly in the European Union, the digital signature is considered very, very important. It is a standard for all countries, and it is valid for all countries. It is having a legal validity. So it is very important that it is done according to the official standard. And actually, there are several standards that are giving more technical details for computing the digital signature. And if you will sign a document in the future, maybe you will do, because when working, it is normal that one is digitally signing a document. It happens, it frequently happens. You will see some technical details that are not exactly the details that we have seen. So it is important now that I can explain you better some technical details. And this is, it is still a topic pending. If you remember, here we said, where is it? Forgery. And we have discussed what forgery is. But we need to discuss key revocation. So maybe before the standards, I should discuss the key revocation. It is possible. No, let me say better. In any case, when you have a certificate that is describing your key, this key is given to you from a start date until an end date. After the end date, the key is not longer valid. Okay? But we just say that is the natural expiry of the key. But maybe I am having this pair of keys not because I am Fabrizio D'Amore, but because I am doing some work, and in my company, in my job, I need to sign because I'm working in some company. So maybe I am the responsible for the company to sign contracts and so on. What happens if someday I'm no longer working in the company? They should revocate the key I have because I'm no longer belonging to the company. So if I go out of the company before the end date of the certificate, the certificate should be still valid, but actually I went away. So they should revocate my certificate. Also, the certificate should be revoked if my private key is compromised. If any other person is knowing my private key is the private key is compromised, and I cannot use any longer the private key. So the certificate also should be revoked. So maybe I lost my private key. Also in this case, I should get this certificate revoked, because if I lost my private key, I cannot use it anymore. So it is useless to maintain the certificate. So what I wanted to say is that there can be a lot of reasons why we want to have the certificate revoked. That means expiring before the end date. So if the expiration, if before the end date, it is revoked. Otherwise, will naturally expire. And after natural expiration, I will buy another certificate. And normally this will cost some amount of money. And okay, I will pay for a new certificate and so on. I will do that a lot of times. And but what is important is that if I am having the original certificate and this certificate is revoked because some good reason, I may still use the certificate, the old certificate, the old version, not yet revoked. I may use it because when I had the certificate, because the revocation, before the revocation, in the several fields, there is the start and the end, no? And then I can use this for signature. It is true that later this certificate has been revoked, but I still have the original copy because I made a copy of the certificate. So I can use the old version of the certificate that has been revoked, and I can use it for the signature. This is why the verification is requesting another step. Let me call it more complete verification. Not only the verification should be consisting of all the steps that I have discussed already. So Bob should compute the digest, Bob should decrypt the signature, should make the comparison, and so on. But there is another condition. Let me write it. Another check. Non-revocation. Bob should check that my certificate has been not revoked. How to check this? In the certificate, I told you a lot of, there is a lot of contents. One of these contents is information about the certification authority. So Bob will ask the certification authority about the revocation. If revoked, the verification fails. If not revoked, the verification can continue and give the answer that I already discussed, and that it was ending in checking whether M prime was equal to M double prime. And so this question about non-revocation, how is it asked to the certification authority? There are two ways. One is the original way. The second way is modern and more efficient. So let me discuss the original way. This is based on CRL, where CRL is certificate revocation list. This means that the certification authority is publishing a digital document containing all serial number of certificates that have been revoked. And there is also the serial number and also the date of revocation. And there is also other information, of course, but this is the most important one part. So I can ask Bob, during the verification, Bob will ask the certification authority by saying, give me the certificate revocation list. I want to check whether whether the certificate of Alice I am verifying is in the revocation list or not. And every 1 week or 2 weeks, the certification authority is publishing a new certification revocation list. The dates of this publishing, they are decided already. I mean that every certification authority will decide when to publish the new CRL, and so that the days of this publishing, they are known to everybody. And all this information are in the certificate, and in the original certificate there is the link for getting the CRL, the dates for the publishing, and maybe there is written that it is published every week or every 2 weeks, on Monday, for instance, and so on. Information on this type. And this is the certificate revocation list. The second way, more modern, is based on a protocol called OCSP. This is a protocol. According to this protocol, if this is the certification authority, Bob can send the serial number of the certificate to check to the certification authority, and the certification authority will immediately answer. Non-revocated or revocated. This is better than the certification revocation list because the CRL is updated weekly, so that information is never really fresh. In this other case, the OCSP is providing a very fresh answer, so that you can immediately know every detail. Also, the link for getting the OCSP response is published in the digital certificate, only in version 3 of X509 standard. If you are using an older standard, there is not possibility to publish this link for OCSP, because OCSP is more modern, so it is described only in version 3 of the standard. In this way, I told you that Bob is obtaining another more complete, a more complete procedure for verification. So, Bob's verification. Computers Digest. Decrypts. Signature. Check for non-revocation. Compare the result of 1 to the result of 2. But if the check for non-revocation is failing, that the whole procedure will be failing, of course. Okay? This is not yet really complete. There is some more detail. Because let's wait. Did you understand? Is it clear?
Yes.
Very good. So no questions or any question? So it is possible in version 3 X5 of 9 version 3, it is possible to add extra fields describing limitations of use. Let me make an example. I am working in Sapienza University. So, as a professor, Sapienza University gave me a certificate. And I am using this certificate for digitally signing registrations of the exams. But in my certificate, there is written certificate can be used only for institutional purposes. What does it mean? It means that I can use this certificate if I doing some work for a university. But imagine that I am doing some private work, just as myself, not as someone in the university. If I do some professional work and later I need to digitally sign, I cannot sign by using this certificate given to me by university. This is why I decided to buy another certificate that I will be using for any non-institutional purposes. And so when you are doing the verification, if you want to be really complete, not only you should do the verification like the process that I described, but you should also check for other limitations, and you should read the certificate and read and understand the limitations, and check whether I am respecting the limitation or not. Okay, but if you understand that all the steps like before, they can be automatic, so you can construct an algorithm doing all the verification steps. Okay, but the last check for checking if there is compliance with some possible extra limitation can be made only by humans. So this means that the verification is never completely automatic, and it is possible that you need to do some extra verification. But in many cases, there are no extra limitations. So the result, the automatic result can be sufficient. But you should check if there are limitations, and if yes, you should check that limitations are respected. Okay? Otherwise, the digital signature is not really valid. This means that if I am using the university certificate for private signatures, the other part will maybe accept my signature because all the steps will be giving okay. But at some point, somebody can say there is an extra limitation that you should be using the certificate only for institutional purposes. So the signature is not valid. So maybe the signature was apparently valid, but it was not really valid, and they can be make invalid the signature. So what I want to say is that first you have to check every signature. Every time you have a signature, you should check the signature. And later I will show you some example on how to check the signature. And you should also verify what possible extra limitation is written in the digital certificate, because it is needed that also other limitations should be respected. Okay? And this is requiring a human approach. Only a human can understand if for instance, if I am using the signature for institutional or non-institutional purposes. And I think that not even a modern AI can do that, can, at least for now. In the future, I don't know. And this is very important. Any question? So please remind these two things. I want to write them. I have already discussed that, but I want to give extra importance. A. Verify every signature. Always. B. Printed signed file has lost signature. The signature is only in the digital document. Never forget these two important critical details. Okay? Let me say now, let me discuss now some practical details. Today, there are two main standards for digital signature. The names of these standards are CADES and PADES. These are the practical standards, and maybe they are signing using the same algorithm, but the way information is collected and managed is different. This means that between these two standards there are some difference. According okay, this is just the name, CADES and PADES. You can divide the names because the part ADES means advanced electronic signature. The first letter is informing you about some other technical details. In particular, let me consider first CADES. This is providing a standard valid in Europe and even in many other countries outside Europe. It is a way for signing, for digitally signing every file. This is important. Whatever is the type of file you want to sign, you can sign it by using CADES. And CADES will provide a result. One file only as a result, with extension .p7m. Okay? What is this P7M? It is a digital envelope. Cryptographical envelope. You can imagine a P7M file as a container, a unique container containing inside original file, signature, certificate for doing the verification, the certificate of the signer for doing the verification. Okay, the format of this container can be also more complicated, but I don't want to give too many details. And for reading this file, we need a software. If you give a P7M file to your computer will say, I'm not able to open this file. You need an extra software for opening this file. And this is the basic information I want to give you about this standard of signature. But I want to stress a detail. What if Alice and Bob they want to sign a contract? This means that there is the need of two signatures, the signature by Alice and the signature by Bob. So let's imagine that the original contract unsigned is M. Let's imagine that the first to sign is Alice. So Alice is signing the contract so that it should be producing a P7M file where there is the contract. And there is Alice signature. And there is Alice key, Alice public key. Okay. The second, it will be Bob to sign the contract. So the P7M container will be more general because after the signature by Bob, there will be the original file, the contract, Alice signature, Bob signature, Alice public key, and Bob's public key. This for telling you that the P7M file can be containing many parts, many components. The number of components is not a fixed number, can be at least 3, but it can be more than 3, okay? And you, in any case, you need an extra software for opening this file. Let me show you. How can I show? I can go to the website and let me show you. So in Italy, this software is given by an agency called Egid. I'm not finding it. Maybe I should make the search in Italian. Okay, you can see here there is a list of software. You can check the names. You can find where this software is distributed, and each of them is allowing to you to check, to verify a digital signature. And not only can verify the digital signature, but can also open a P7M file and extract the information contained in the file. In particular, extracting the original document that has been signed by the parts. And you can extract the document and get the document. And also ask for the technical part of the verification. The only part that it is not obtained is the check whether the certificate has been used according to the purposes of the certificate. And this is needed human contribution only. Okay? There is a huge list here, but this is not complete, not even complete. It is there is a longer list. Let me check whether the site is also in English. No, it is not also in English. But this software is approved by the Italian government. So I suggest you remember this detail. It is also possible to use some websites that are providing service about verification of digital signatures without downloading a software. In particular, one software for verification is offered by Sapienza University. And how to see that? This is the software from Sapienza for doing the verification, for extracting the original document. Now the website is showing nothing because I'm not yet added any signed software, of course. This is the P7M. There is also another standard, because you remember there is CADES and PADES. According to CADES, you can sign whatever document. In PADES, you can sign only PDF files. Okay? You cannot use PADES for signing other file. Only PDF files, because this is important, and it is still very general, because a lot of documents, they are written in PDF form, and you should just you need to sign a PDF file. If you have a PDF file, you can decide if you want to sign it with the CADES or PADES. You can use both, because CADES is for whatever type of file, also for PDF. But if it is a PDF, it will be more natural to use PADES, because PADES is more special for PDF files. And the result, namely signature certificate, it will be still in a PDF file that will be opened by whatever PDF software. This is important, because you don't need extra software for opening the original document. It is sufficient whatever PDF viewer, and you can open it whether it is signed or not is signed. But some PDF viewers are able to check that the file is signed. In any case, all the software that is providing the possibility to do the verification for extracting the original document is also able to verify the PDF file that has been signed. This means that if the file is signed, you can you can in any case open the file, so there is no need to extract the original document, because you can view the original document even if signed. But if you want to verify the signature, then you still need the software for verification. And you should load the document in the software, and you should ask for verification, still being valid the fact that you need to respect every possible other limitation that is introduced in version 3. Under a legal point of view, both PADES and CADES, they are valid. The two standards are the most used by humans. There are other standards mainly used by software, because it is possible to ask to a program, to an application, to make a signature. And when applications make a signature, generally they prefer other standards that I don't want to describe now, because not really interesting. And there is another last thing I want to say. So you understand that one thing is the theoretical part I have described to you, where when producing a signature, Alice is sending the original document and the signature. Then there is the standard, the official standard, that is including all information. In the CADES case, it is using the cryptographical envelope, so that you have a P7M file. In the case of PDF, there are just extra PDF lines. This is the PDF file. There are some extra lines containing information about the signature and all what is needed. But in the case the viewer is not able to check the signature, the viewer will be just ignoring the extra lines, so that you can view the signed file in a natural way. This is why we prefer to use PADES for PDF files. And when I see someone signing PDF files with the CADES, I say, that is not natural, but it is not wrong. Okay? There is another point I want to underline. Local signature versus remote signature. In the case of local signature, signer is having the private key. Maybe it is on some device like a smart card. In this case, internet connection not needed. In the other case, remote signature, provider is having the private key. This means that the original signer is not having the private key. But you know that the private key doesn't need to be compromised. So the provider, if the provider is having the private key, the provider should be not able to see the private key. This is why the private key is encrypted. With password known to signer. So if the provider is having the private key, the provider cannot use the private key because it is encrypted, and only the signer, the original signer, that is the owner of the private key, is knowing the password. When the signer needs to do a signature, the signer is communicating to provider the password. The provider will accept the password, will use the password for decrypting the private key, then will make the signature on the file, and then will immediately forget both the password, and the key. Okay, and this is checked by the government that is analyzing the operation manual of the provider for verifying that it is really it is really forgetting the key, the private key, and forgetting the password. And in addition, there are some checks that the government is making on the provider for ensuring that this is verified. So you understand that for doing that is internet connection is needed. Because the provider, the signer should be communicating to the provider two information: the file to be signed and the password for decrypting the key. And they are information needed by the provider, and this information is communicated by an internet connection. By using the internet connection, the provider will be able to do the signature. And after the signature, the provider also will remind the owner that a signature has been done by sending an email. For security reason, the signer will be informed. But in general, the signer is already informed because the signer just used the service. But in case of some abuse, the signer will know immediately. This is the remote signature. Both PADES and CADES can be local or remote. And in my case, for all types of digital signature I use the remote version because I find it very comfortable to have my private key stored in the provider in a safe way, in safe and secure way. Any question? Okay, no questions. And I think this is the last time we are meeting here online, because this is the 5th time. And as you know, there will be a final test that you will need to to pass, and we will organize the final test as a competition. You will receive information about that, but it will be a friendly competition where we will have to cooperate, and it will be fun, and I hope you will have fun with some competition. And in this competition, you will need to use information about cryptography and information about coding that you have learned with Paolo Franciosa. And as you know, while considering these fields, we have also considered the mathematical information you have seen already with Apolloni. I don't remember exactly the name. And I hope you have enjoyed these meetings, and you can contact me. You know my email, but I want to write it again. This is my name.
Oh, and sorry to ask, this competition will be physically in Rome when we meet?
It is not really needed because the competition can be done also online, but maybe the organizer want you are doing when we meet. Yes, you should ask the organizers.
Okay, thank you.
This is my address, and you can write to me, and in any moment. But when you writing to me, if you want to write to me, ensure that not only you give to me your name, but since I have many students in the university, you should also remind me that you are coming from this project. Otherwise, I will make confusion. So I want to thank everybody, and it was very nice to be with you. I hope to meet all of you very soon. Thanks again.
Thank you. Bye-bye.
Bye bye.
Thank you.
Thank you.
Thank you. Goodbye.
Thank you.
Thank you.
Good evening.
Thank you. Bye.